So let us talk about open methods. So in bracket methods, we have seen that to be able to solve the problems, you have to give an interval, okay, which I think is a kind of disadvantage of bracketing method. Okay. On contrary, in open methods, you don't have to give any interval. Okay, you just have to give a starting value, and this starting value is up to you. Okay, but I'll tell one thing. I'll tell you at this point is that the kind of starting value that you are going to select is going to be very important in open methods. Okay, so when you talk about open methods, again, there are two methods. One is Newton-Raphson method, and the other method is secant method. There are other methods as well, but I'm just going to discuss these two methods. So let us talk about Newton-Raphson method. So again, Newton-Raphson method is very simple. Okay, you just have to use one single equation, which is xi plus 1 is equal to xi minus of fxi upon f dash xi. Okay, where I is the iteration. So the value from the previous iteration, the value of the current iteration is going to be value from previous iteration, the function value of that iteration, and the derivative of that function substituted by the value at that iteration. Okay, so this is the Newton-Raphson method. Okay, and it's very simple. So let us discuss this, and once we discuss this, then we'll see the secant method. So let us solve one problem here. Okay, and this time I am going to take a transcendental problem which involves an exponential. So the problem says that a function is given, and that function fx is equal to e raised to minus x, and we have to find out the roots of this function. Number one, using Newton-Raphson method, okay, they have given us the initial value, the starting value. So you have to start from somewhere when you talk about Newton-Raphson. So they have given x0 as 0, and you have to solve the same problem with secant method. Okay, and the starting values they have given as x minus 1 is equal to 0. These are the starting values. Also, they have given us the true value. The actual value of the root is 0.56714. Okay, so let us solve this by Newton-Raphson method. So first of all, what is the function? E raised to minus x. And what is the formula of Newton-Raphson? It's very simple. Once you see it, you'll remember it. The formula of Newton-Raphson is xi plus 1 xi minus fxi upon f dash xi. So when you see this formula, you'll realize that you are going to need a function and also derivative of the function. So derivative of the function is, it's easy, you just derivate this. So you'll realize it comes out to e raised to minus x, because derivative of e raised to x is e raised to x, and derivative of x is 1. Once you find out this, you can substitute this value in this. So x plus 1 is going to be xi. Okay, and what is fx? E raised to minus x. Okay, since we are writing about with for I, e raised to xi minus xi upon minus of e raised to xi minus of 1. Okay, so I would follow a tabular method where where the first column is going to be your iteration. Okay, and the second column is going to be your xi. Okay, and this is going to be xi plus 1. So let us start with the zeroth iteration. So understand one thing, in Newton-Raphson method you need some initial value, and that initial value, if you're solving a problem, will always be known. Or if you're solving a physical problem, based on the physical setup of the problem, you can think of an initial value which is going to lead to convergence. Okay, but when I'll be giving you a problem, I'll be giving the starting value as well. So you can just the starting value here is 0, so x0 is 0. So now what we are going to do is we are going to put x0 is equal to 0 here, and you will find out the value of xi plus 1. So once you substitute everything, okay, one more thing I need to write down here is true percentage error because the true value is given. So once you substitute the value of xi in this equation, the value of xi plus 1 that you're going to get is going to be 0.5. Okay, and if you subtract that from this and find out the true error, it's going to be 11.8%. Now I hope I don't need to tell you what is the formula for true percentage error, because it's been high time now that we have used it number of times. So this is it. So the first, then iteration number 1, this xi plus 1, that is the next value, now will become the previous value. Okay, for this iteration this will become previous value, and then using this previous value we are going to find out the current value. So again, now what you're going to do is you're going to substitute 0.5 in this equation here, 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 and here, and we are going to find out the value of xi plus 1. So once you do that, you'll find out the value of xi that you're getting is 0.566311. Okay, and the percentage error is 0.14%, which is good, but we are dealing with 2%, so it's always better to get it very close to 0. So we'll go to the next iteration. Okay, this value will become your previous value now, and you substitute this value in this equation and find out the current value. So once you substitute, you will find out the value comes out to be 1432. Okay, which is approximately, if you see, okay, in fact it's very close to 0, or it's almost 0. So it's almost 0%. Obviously I have truncated the number at this point. If I would have not truncated, then there would have been some value of percentage error, but for this it's going to be 0. Okay, so yes, this is how you are going to use Newton-Raphson method to find out. So this is one equation. If I give you any equation, I think you should be in a condition to solve it using Newton-Raphson method. There is another method that is known as modified Euler method. Modified Newton-Raphson method. I'm really sorry. That is modified Newton-Raphson, which is, as the name suggests, modification to Newton-Raphson method. So I can give you the formula. If you're curious, you can just try this. The only thing here is that instead of single derivative, we use double derivative, and the formula, if I can recall it correctly, is yes, I think I'm correct. Sure, let me check it again. Yeah, So this is the formula. So if you're curious, you can just check it. I'm not going to teach this thing, and